anytime fault-tolerant adaptive routing for multi-robot teams. Information gathering is fundamental in several applications, for example, environment monitoring and search and rescue missions. Generally, these problems involve one or more robots collecting data from a set of predetermined target locations. When considering real-world scenarios, we have to take account some constraints, such as the limited budget of robots and sensing points with different importance. This means that some locations have more valuable information to be captured than others. So we need to be concerned about possible robot failures during the execution of the plan to ensure that these important locations are visited. For this reason, we believe that a good alternative for planning missions to information gathering is to model the problem as an instance of the Correlated Team Orienteering Problem. And in this paper, we present a novel anytime method for efficiently adapting the routes determined in a CTOP instance solution in order to minimize the impact in the collected reward in case of robots failure. The OP formulation considers a set of locations with different associated rewards and vehicle with a restricted travel budget. The goal is to select and visit the most profitable subset of locations in order to maximize the total accumulated reward, where the select path must respect the budget. The OP can be seen as the combination of knapsack problem when determining the subset of problem to be attended and TSP, choosing the order to visit this point. A direct extension of OP classic formulation is to consider the use of multiple agents working as a team. This variation is known as Team Orienteering Problem, and its solution becomes a set of routes, one for each team agent. In this paper, we adopt a variation of TOP known as Correlated Team Orienteering Problem. In the correlated version of the problem, when visiting a given node, it is possible to get partial information about its neighbors. For this reason, Coop and Settop have been used in several applications to model sampling or information gathering tasks. So in this paper, we choose to model the problem as an instance of CTOP. Ciokas and Lane proposed a heuristic to solve CTOP. The results show that the reward captured was near to the optimum and about 300 times more efficient in time execution. However, the study instance had less than 100 nodes. Several studies describe OP variants where uncertainties are associated with one element of the problem. However, uncertainty in the robot execution has not yet gained proper attention. This aspect is critical in real-world applications, since it's common for occurring failures that prevent a robot from completing the mission as planned. This paper takes a step towards understanding the operation in scenarios where team members may fail and not fulfill the initial plan assigned to it. Such situations can occur when some robot sensors stop working or when it suffers some damage. We can divide an information gathering mission in two phases, planning and execution. The planning phase consists of to determine a set of routes, one for each robot, in order to maximize the team's reward collection, as shown in this equation. However, in this paper, our focus is on the mission execution phase. Therefore, our problem is defined as, given a set of robots and an initial plan, the goal is to minimize the impact of robots' inspection actions in the team's final captured reward. In other words, to minimize the impact of unexpected events in the assessment of the equation. We present an efficient strategy that locally makes minor routes adjustments, minimizing the global impact of failures. The idea is to adapt only a segment of the route that is closest to the robot. As we have a budget limit, we remove nodes to increase the budget and insert new nodes to increase the collected reward. The first step is to evaluate the current route and copy the route to make adjustments to that copy. This ensures that the robot's current route will not be affected. In the figure, the darker blue node represents the current position of the robot. The light blue nodes are already visited nodes, and the orange nodes have not yet been visited on the road. Then, we enter the node removal step. In this example, we consider a segment of size 15, the green nodes, removing 20% of nodes. Therefore, 3 nodes will be removed from the segment. The nodes chosen to be for removal are those that least contribute to the reward collections in the segment. In the figure, it is the nodes indicated by the arrows. Once the node is chosen, it's simply removed from the root. The next step is the insertion of nodes. In this step, we analyze only the nodes within the shaded area. The size of its area is defined by parameters and serves to limit the number of nodes analyzed to improve the performance of the method. We choose the nodes that will not exceed the budget and will most contribute if inserted in the root. The number of nodes inserted is not related to the number of nodes removed. In this step, we insert nodes as long as we have the budget for it. In this example, we insert 2 nodes and have no more budget to insert anymore. In the end, we evaluate the reward of the new root and compare it to the reward of the robot's current root, which is the root before the modifications. Once it is done, we choose the root more profitable and set it as robot's root from that point on. In our experiments, we compute the initial plan using the genetic algorithms proposed by Ciocas and Lane using the default parameters. The figure depicts the initial roots planned using the method for 3 robots. As this method is a heuristic, it might produce suboptimal solutions. Therefore, to minimize the impact of these suboptimal solutions in our analysis, we further improve the initial planning by also applying our methods at the beginning. Our method is sequentially executed 5 times to ensure sustainable results. We can see in the table that our method is beneficial even for this case where there are no failures. Given the optimized initial plan, we seek to analyze the reward our method would get to recover when a robot fails during the plan execution. In all tests, we consider the following strategies: non-adapt, ignores the failures; replanning, reruns Ciocas and Lane methods; and our strategy, or adapt, applies our end-time method to adapt the roots. The replanning strategy demands the mission to stop while a new plan is determined. We generate a new CTOP instance considering only the nodes not yet visited. With the new planning, we merge the paths already taken in the mission with the new planned routes so that the robots can continue the mission. Unlike the replanning approach, our algorithm works by adapting the section of the route closest to the robot without having to stop the mission. Once a failure occurs, the method begins to be applied to all routes of the remaining working robots. Each time the robot moves from one node to another, we execute the procedure to update the next route segment until the robot finishes the mission. To verify how our method responds at different mission stages, we force one robot to fail at the beginning of the mission or after completing a percentage of its route. To create the worst case scenario, we will remove the robot that has the route with the highest reward in the initial plan. In the left figure, you can see when the robot fails at the beginning of the mission at 10%, 30%, 50%, and when it doesn't fail. We can see in the green line that when the robot fails at the beginning, the drop in reward is very high, and that the further towards the end of the mission, the less reward is lost. Also, we can see that replanning the routes are better than our strategy of just adapting the route, but both are much better than ignore the failure. In the figure on the right, we see the time spent by each strategy. We can notice that the sooner the robot fails, our strategy spends less time than the replanning strategy. This is because the further ahead in the mission, the more nodes will have to be analyzed by replanning strategy, which considers all the nodes not yet visited. And this does not affect our method directly. The time spent by our method is conditioned to the number of active robots in the mission. We also analyzed the case with more than one robot failed during the mission. The robot with the highest reward in the initial plan fails at the beginning of the mission to enforce the worst case scenario. We can see in the figure that the reward captured by the team at the end of each mission when the second robot fails at different plan progress percentages. Again, we see that replanning is the best option, but our method can also recover much of the reward that would be lost if you ignore the failure. About the time, the closer to the end of the mission the second robot fails, the less time is spent by the replanning strategy. and the greater is the time spent by our method. The more to the end of the mission, the fewer nodes the replanning strategy has to analyze, so it spends less time. In our case, when more to the end of the mission the robot fails, it means that for a longer time its route was being adopted. Remember that the two robots start the mission adapting their routes due to the failure of the first robot at the beginning of the mission. To test our method in a scenario where the use of replanning would be impractical, we did a simulation on an instance with 900 nodes and a team of 10 robots. In this experiment, we considered that up to 9 robots could fail. We can see in the reward graph that our method can recover a reasonable amount of reward regardless the number of robots that fail. The time graph reinforces that our method has complexity that depends on the number of active robots. The smaller the number of robots that fail, the larger the number of active robots executing the methods and the more time spent. Together, these results demonstrate that our method is robust and appropriate option for cases where robot failures are possible. Another advantage of our method is its anytime property. While the procedure is running, the robots already maintain a viable route to follow, and they have pieces of their routes adjusted to optimize the collected reward. In this paper, we propose an anytime algorithm to adapt the robot's routing during the execution phase of missions planned as an instance of the CTOP. Experiments show us that in the case of team members' failure, our method is as efficient as replanning the robot's routing. Moreover, our method spends less time and does not have to stop executing to replan the route. Future work includes considering different types of robot failures, for example, sensing or communication failures, that do not necessarily remove the robots from the mission, and we also intend to extend the method for heterogeneous teams. Thank you.